Okay, and in this last lecture, we're going to talk about clustering, outlier analysis, and association rules. So clustering and outlier analysis is kind of related. So clustering are grouping the data points or data objects that are similar. And outliers are the ones that does not fit in any particular group. So once you do the clustering, there's a chance if there's anything that doesn't quite fit in any group that becomes the outlier. And association rules is a bit different. And it's about two things that happens more often than the random chance. Okay. And we'll see some examples later on, which will make it makes it more sense. Okay, and we're going to start with the clustering and outlier analysis. And we mentioned these two are related. Okay, and so I'm not going to go into so this is one of the definitions, but the general idea is you want to group the items in your data set. And so the similar ones are in the same set. So the objects in the same cluster and should be as similar as possible. And then objects of different clusters and should be as dissimilar as possible. Okay, so these are some examples, might be the data set you have and how they look like in the, say, did we talk about projection? I can't remember now, but let's say this is how they spread. And you can roughly, if as a human we can see, so someone might say this has 3 clusters and this is 1, this is second one, and this is third one. But in this case, there's no very clear boundaries. And as they kind of all overlap each other. And then for this one, you might say this one is cluster, this is another one, this is the third one, and this is maybe the fourth one. Yeah. And this is the one where the cluster is not necessarily like a kind of convex or maybe like a, say, circle type of shape compared to these ones. You can see people might say this is one cluster, this is another one, a third one, and fourth one. And then similarly here. Okay, and for this one is slightly different. And it says it might have a, what call here a hierarchy. And so you may say, this is one cluster, this is another one, second one, and this is third one. But within the third one, you have 2 smaller clusters or groups. And again, for this cluster, within it, you have further, can easily divide it into smaller ones. And so this might be a hierarchy of clusters. Okay, and so okay, and closely related is the outlier analysis. And so outliers are the ones which does not quite fit into any cluster. And so, for example, you can say this one, and you can kind of, I say this point is belong to this cluster. That's probably the closest one, but still you can quite easily see it's quite different from all the other points in this cluster. And so you might say this is an outlier. And also, this is called a local outlier because it's quite different from a cluster next to it. But if you look at this as an entire data set, and it's still kind of within the range. Again, so this is a bit vague. What is within the range is completely for you to decide. Whereas if I look at these two, and they are further away from the entire data set. Let's say this is the entire data set. They're much further away from the majority of the data in the data set. So these two are called global outliers because they don't really have any close neighbors at all. Okay, so now we look at some kind of practical examples where you were using clustering and outlier detection. One of the first application domain is marketing. And so you have a database of like a company, you have a database about all the customers you have, including, for example, the name of the customer and then what they bought before. Okay. And then you might want to find a group of customers with similar behaviors. And then you can use this to do for marketing purpose. So for each group, and they have similar behaviors, and you can maybe targeting that type of behavior. And for example, and you can, I don't know, this is, and maybe this is a group of young female customers, and they are more interested in, say, the fashion and cosmetics. So maybe when you do the marketing, you might be targeting that group to provide more information about fashion or cosmetics. And also you might find some customer with unusual behaviors. And these might be someone's, and maybe say taking advantage of the systems, and you might want to treat them separately and pay more attention to what they do. Okay, and these are some other examples when you would use clustering. So determine user groups on the web. So this is based on the, say, what pages user look at or what website they visit as information to group these users. And again, it might be useful for targeting or for other type of purposes. Or you can look at, say, just large sets of documents. Say you might have a collection of different books, and you might group them depends on the content of books. So there might be, say, a fiction or non-fiction writings, or these are the textbooks for programming. So these are different possible clusterings you have. And this kind of clustering can be hierarchical. So you may have, okay, all these are programming books on programming languages. And then you have different, so that within it, you would have clusters for different programming languages. So this is for Java, that's for Python, and different languages. And then, for example, for each programming language, you can further divide. So these are for beginners, these are for more advanced users, these focused on, and developing apps, and so on and so forth. Okay, and similarly, you can also grouping and where the data itself are pictures. And so the picture itself can be satellite images, or just could be the photos you've taken on your phone or camera, and you can try to group them. You say, okay, these are all has peoples, these are all landscape, and these are all within landscape, or these are all, say, mountains, etc., and so on and so forth. Okay, and in terms of the clustering methods, and there are lots of them. So as I see in the previous examples like this one, so exactly what makes a cluster and what is an outlier is not clear-cut. There's no like a single rule says, okay, I guess most people would agree this should be in one cluster. But I guess, say, for this one, and some people might think it's not a cluster, some people might think it is, and whether these points belongs to this cluster or not, again, is up for discussion. And so again, there's no single one rule, so that's the only way to do clustering. And also there are many different results for, many different methods for clustering, and sometimes they don't always give the same results. So the results would be different. It doesn't mean one clustering is better than the other. This only knows if you know the answer. For example, and you know there are, say, 5 clusters or 4 clusters in this data set, and this is the cluster 1, these are cluster 2. These are kind of like the previous knowledge or in the machine learning sense, or the, for example, we talk about doing prediction or classification, where you already have the labels. And here the labels will be which cluster a point belongs to. And if you know those answers, then you can measure whether a method is good or not. And then just as the classification methods, you would have different results, just depends on, say, are you using decision trees or KNN or some other method? And then they will give you slightly different results, not always the same. Okay, and so the first type is the partition-based method. So that divides the entire data set into several groups. These are usually not non-overlap. And Kmeans is probably the most common, most famous one, or most commonly used, partly because it's simple. And the result is always good. And then there's some other ones. Okay, and there's also linkage-based methods. So these are looking at the linking kind of relationship between the data objects and use that to decide which whether the points are or the data objects are within the same class or not. Okay, there's also density-based method, and DB-scan is actually a linear scan. But so, for example, this can be kind of example of a density-based cluster. You can see this area is very dense compared to the areas around it. So this might be considered as a cluster just because they are much dense in the surrounding areas. And similarly for this one. I mean, in that sense, it's a bit similar to we as a human, how we see visually if there's a cluster in the data set or not. Okay, and there's other methods like self-organizing map, which just depends on similarity between the points next to each other, and they will move. We're not going to cover those. So we're going to cover the red ones we highlighted here. Okay. Okay, and so we start with the partition methods, as we said, and this tried to kind of divide the entire data set into several groups, each one as one cluster. And then what is they want to, the kind of way they achieve a clustering is try to minimize the cost. And what exactly the cost is depends on the method itself. Okay, and so in terms for the K-means clustering, and you will have to decide what the K is. And so, for example, you think, look at this one, I think there's 1, 2, 3, 4. So I say K is 4. And then you choose one point to represent each cluster. And then you try to optimize these, which point is used to represent each cluster, and assign each object to its most or the closest cluster. Okay, again, this is quite abstract. And so, for example, you might say I have 4 clusters and I choose one point to represent each cluster initially. And these 4 points are not necessarily the best to represent. For example, they're not necessarily in the middle of the cluster. For example, and for this one, I picked something here as a representation. It belongs to this cluster, but usually, intuitively, you want to pick something in the middle of the cluster as a representative. And then you try to optimize this by reducing some cost, which we'll talk about later. Okay, and then in terms of the representatives, and you can use the mean of the cluster. So this is like averaging the X and Y coordinates of all the points, and you get a center. And so this is a central point, and it might not exist. It might not be a data point from the data set. Again, come back to this example. Let's say we're going to calculate the center point of this one. or the mean of this one, you just calculated the average x of all the points and average y of all the points. You might say this will be the center point. And that kind of point, that's not a point which exists in the original data set, but you will use that to represent the entire cluster. Or can use the median. So in this case, you actually pick a point and which you think is in the middle of the cluster to represent. Or you can use the density function. So this is, again, just look at the distribution of the points where it is the densest, and use that as the center of the cluster or representatives of the cluster. Okay. Yeah, and so these are the steps of the K-means clustering. We kind of talked about them already. And so into partition your entire data set into K and subsets, and you need to pick the K. The algorithm itself will not suggest what the K should be like. And then you compute the seed point at the centroid of the cluster. So basically you pick one point to represent each cluster, or pick one point as the center in some sense. So this can be mean, can be median, can be the density. So essentially there's these ones I talked before. Okay, and then assign each point or each object to the cluster with the nearest seed point. Okay, and so if you, for any cluster which doesn't have for any point which doesn't have a cluster yet, just check, say, which of these seed point is closest, and then assign that point to that particular cluster. And then you go back to step 2. Okay, and because once you assigned a point to a cluster, then the mean point or the median point of the cluster will change, because now the cluster becomes a little bit bigger, has new points in it. I need to recalculate what the mean is. And then you do the assignment again, and so until all the points have a cluster. Okay, and so this is what the algorithms would look like. And we're not going to go through the actual code itself here. You can have a look if you're interested. Okay, and so the K-means is one of the most popular partition clustering methods, or just even in clustering in general. And because it's relatively simple the idea is quite simple, and so it's easy to implement. And also it's relatively efficient in terms of it doesn't take very long to run the algorithms. Okay, so we're introducing some numbers here. So the n is the number of data objects, so that means the number of data points you have in the data collection. So the K means the K, which is the K means in the name, is the number of clusters. And the T is the number of iterations. Okay, and so the iterations, it says you can do the clustering, as we said, complete the entire process. So here, when you go back to step 2, is one iteration. Okay, and so usually the number of the clusters and iterations are much smaller than the number of the points, total data points. And then for each iteration, you have to go through all the points. And then in each iteration, you have to check for the distance to all the clusters. So the total time you need to compute is O, T, K, and N. So if you don't quite understand what this big O means, that's completely fine. That's an indication of how long the algorithm needs to run. And usually that depends on, say, the number of data points you have the larger the data sets you have, the longer it will take. And in this case, it also depends on how many clusters you have and how many iterations you run. Okay. So this is kind of like the advantages of using Kmeans. It's easier to implement and doesn't take very long to run, but also it has some weaknesses. And so first, it often terminates at the local optimum. And local optimum means, and it's not the best possible solution. But if you only look at a small subset of all the possible solutions, it's the best one among those. That's the local one. And obviously, you want to find the opposite of this, which is called the global optimal. So that's the best result globally, but that actually is quite difficult to do. So it's applicable only when mean is defined. For example, if you have categorical data or nominal data, it's difficult to know what the mean is. For example, there is an attribute which indicates it's the color of the product. And then how do you calculate the average of the colors? There's no good way to do this. Okay, and then you need to specify the number of K, and this is a bit difficult unless you have some knowledge about the data set. And if you pick the wrong number of the K, for example, there are actually 10 clusters in the data set, and you said there are 5, then you're going to missing some clusters or grouping unnecessarily the class together. Okay, and then they are not very good at dealing with noisy data and outliers, and because all the noise, which kind of is similar to the outliers, are treated the same as the other points when deciding which class it is. And finally, it's not suitable to discover clusters with non-convex shapes. So essentially, let me go back here. And for this type of clustering, and for example, you might think this one is a cluster and this one is a different cluster. But for the K-means, because it's only calculating the distance between the points, so it actually will think maybe, and this is one cluster because they are closer to each other, whereas this part is a different cluster because they are further away from here, rather than thinking this whole thing is cluster and this one is a different cluster. So these are the shapes called non-convex shapes or concave shapes. Okay, and so again, one of the disadvantages we mentioned is they are not very good at handling noisy data or outliers. And it's so because every point is treated the same. So the objects with extremely large values may substantially distort the distribution of the data. Yeah. So for example, again, let's go back here. And for example, so if you're using K-means clustering, and it might decide all these points belongs to one cluster, because the algorithm will try to find a cluster for every point, even if you might think it's we as a human might think it as outlier. So because we're taking these two things into account, if you calculated the mean of this entire group, the mean might be somewhere here, where actually it's not really the center of the cluster, where actually here there's no point at all. And you might say it's not the best representative of this cluster. And it's more likely if we treat these two as cluster as outliers, and then you might calculate the mean of these points and somewhere here, that maybe looks like makes more sense. Okay. And so instead, for this type of problems, so instead of using the mean, you're going to using the equivalent of the median. So it's called the Magnoids. And so that's the mostly centrally located object. So that's almost like the equivalent of the median when you calculate, when you have say a sequence of numbers. So that's the number in the middle. So in this case, you have 2 dimensions and you want to find the point in the middle. And in that case, and it's more likely to be somewhere here rather than here, because you look at the X and Y distribution, you pick the ones that's in the middle. So that's more likely to be actually in the middle of the cluster rather than influenced by the outliers. Okay. And so this is examples of this kind of equivalent. The Magnoids or the equivalent of medium. So if we have these two and clusters, and so this one will be the medium of this cluster, whereas the mean might be somewhere here, but there's no point there. So they pick the one that is closest to the, and not closest. And then similarly, and for this one, and this will be probably the medium, sorry, the Magnoids, and because that's kind of closest to the medium of the cluster, or that's the medium of the cluster. Okay, and so that's about the K-means clustering. And next one, we're going to look at the linkage-based method. Okay, so here, and essentially the linkage-based is hierarchical clustering. And so the K-means clustering does not have hierarchies. And so if you said I have 4 clusters and it will give you 4 clusters, these 4 clusters are on the same level. Whereas the linkage and based methods and by default will give you a hierarchy. So this is you've probably seen some kind of thing like some diagram like this before. And this is also known as dendrograms. Okay, and so this is essentially like a tree, and this will be the root, and this will be called the leaves. Okay, and the way it works and is actually bottom up. So it starts from the individual points and they try to group them. And then after you've done the first grouping, and then you group the groups. So you let's say, okay, and this is one group, and this is another group, and this is third group, and this is fourth group. And once you've done the first time grouping, and then you treat each group as a point as well, you do another grouping, and then maybe this two, now group with this one, and now this entire thing becomes a group, and then it's further grouped with this one, and so on and so forth, until there's only one group left, and you get this kind of hierarchy. Oh, okay. And in terms of creating this hierarchy, what we mentioned before is bottom up. And so you start from the individual data items and try to group them. And then you can group the groups and so on and so forth until there's only one group left. And you can actually also do top-down, and where actually you start from the entire data set, and you divided that into a few groups first, and then within each groups you further divide. That's also possible. And based on my personal experience, the bottom-up construction or the bottom-up method is more common. Whereas for the top-down, and you can use something like a Kmeans, and you can first run the Kmeans, which divide, let's say, the entire data set into 5 different groups, five clusters, and then within each cluster, you can run Kmeans again, and then it will divide it further into a number of clusters, and so on and so forth. Okay, so this is kind of the method we talked about before. So this is and the single linkage algorithms, or also this is the bottom-up method, or sometimes it is called the hierarchical clustering method. And you start with your data points. In this case, we have 9 points, and you calculate the distance between every pair of points. And so the distance between 1 and 2, 2 and 3, and 3 and 4, sorry, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1, 6, 1, 7, 1, 8, 1, 9. And then 2, 3, 2, 4, 2, 5 all the way. Okay. And then once you calculate all the pairwise distance, and you choose 2 points, which that has the smallest distance, and merge them or form a group. So let's say after we calculate all the distance y, and then 2 and 3 has the smallest distance, and then 2 and 3 becomes one group, and you repeat the process again, but this time 2 and 3 is treated as 1 point rather than 2 separate points. And so you calculate distance between 1 and group 2 and 3. Basically, you calculate distance of 2 and 3 to all the other points. And then you again do a comparison to see which pair has the smallest distance. And maybe now, in this case, 5 and 6 have the smaller distance. So these get into a one group and treated as a new point. And you repeat the process. So every time you group 2 points, and each point itself can be a group, and you repeat this process until there's only one thing left. Okay, and one thing here is, and once you merge the points or form a group with multiple points, and you need to be able to calculate the distance between the group and to other points, or between this group to other groups. And this is how so this is one way of deciding this. And so it says distance between 2 clusters is the minimum distance and between a point in the first cluster and a point in the second cluster. Okay, and so this is one way to do this. So that means the distance between the two clusters is the short distance coming from one point in the cluster to the other. You might do the other, say for differently, you might calculate the average distance between 2 clusters, and so on and so forth, which will basically the distance matrix you decide will affect the clustering. Okay, and you can also, instead of calculate the minimum, and you use the maximum distance between the 2 clusters as the distance between 2 clusters. Okay, and again, some strengths and weakness of the linkage clustering or linkage-based clustering, and especially for the ones we just talked about. And it does not need to know the number of clusters beforehand. You don't need to tell the algorithms. And it gives you not just one clustering, but a hierarchy of clusters, as we've seen before. And you can obtain the clustering from dendrogram by performing a cut. And so what it means is you can say, okay, if you can take a cut roughly here. Let me see if I can. How do I get it? Oh. Try to for example, you can cut it here, and in this way, when you cut it here, you get two clusters. So this side is one cluster, and this side is different cluster, and then just depends on where you make this cut. Make this cut in the hierarchy, you get different number of clusters, and so you can choose, depends on your need. You can make a cut roughly here. Then you have 1, 2, 3, 4, and 5 clusters. And as you move down, you have more and more clusters, and you can do a cut here. Then you have a clusters. Each cluster only has 1 point. Yeah, okay. And so that's what this part means. Give you a hierarchy of the clusters. Yeah, and you can you can obtain a cluster with any number of a clustering with any number of groups. Just depends on where you perform a cut in the hierarchy. Okay, and so yeah, the merge or split cannot be undone. So if you remember, if we do a bottom-up and approach to construct the hierarchy, and every time we need to decide which 2 nodes get to grouped into a cluster or become a new node, and that process is not reversed. So sometimes, and it might not be the best way, but that's something you cannot reverse even later on if maybe the result doesn't turn out to be the best. Again, it's sensitive to noises. If you have an outliers included, it would also affect the quality of the clustering. Okay, and then it's inefficient. Its runtime complexity is at least O(n) squared, and so that means because you need to compute the distance between every pair of nodes, and so every single node have to calculate this distance to all the other nodes in the data set. So in total, you have to do that distance calculation about O(n) squared times. So if you have 10 nodes, and the number of distance calculation you need to do is in the order of the 10 square, which is 100. Okay, and so this is slower. And then the Kmeans clustering, if you remember, so the Kmeans clustering, and this is about O, T, K, and N. So here, the T and K, which is number of iterations and number of clusters, and it's usually much smaller than N. So this number usually is much smaller than O(n) squared, which is the time needed to run the linkage based or the hierarchy clustering. Okay, and so that's the second type. Now we move on to the last type of clustering we'll cover, is called density-based clustering. Okay, so intuitively, you just say, okay, if there's a densely grouped point, and that will be treated as a cluster. So it's not just using distance, but also actually looking at density into, say, for a fixed amount of space, how much points you have. Okay, and the advantage will be, say, you can actually use this to cluster and of arbitrary shapes and more robust to noise, because the noise will be further away or in the area which is low density, and it will not be included. And it's also faster to run compared to the hierarchical, the linkage-based method. And relatively speaking, so again, if we go back here, I think it's no. Yeah. And so for this type of clustering, and if you're only using the distance between the points to cluster, which is the case for both Kmeans and the hierarchical or the linkage based, so these points are going to be grouped together because they are closer compared to this point and this point. But if you use the density based one, and these points are going to be put together because they are closer to each other, or they're all within the same area, which have a denser and distribution, has more points compared to the area next to them. Okay. There's some examples here. Yeah. So for this kind of clustering, and the shape of each cluster is called convex. And so these one would work well with the Kmeans or hierarchical clustering. Similarly, it also works with density based. Whereas for these ones, it's usually not going to work well with Kmeans or hierarchical, because they only consider the distance between the points. As I said before, say the red points here is quite close to the blue points here compared to the red points here compared to these red points. Whereas all the red should be in one cluster and the blue should be a different one. Okay, and these are the actual algorithms. I'm not gonna try to explain that, and if you're interested, and you can have a look. And so that yeah, and it will just take too much time and to explain all this. But also I think the main point you want to take is if you want to do clustering on your data set, and you might try different ones, and you might even try to visualize the data set first. For example, you would have a kind of intuitive idea of what the shape of the cluster would look like. And if it looks like something like this, and you might, so that makes you aware, you probably want to try something which is the density-based method, dbScan or other density-based method, which would potentially works better, and compared to distance-based like or linkage-based, either like the Kmeans or the hierarchical clustering. Okay, so that's all we want to talk about in terms of the clustering methods. Next, we're going to talk about another part, and is about the association rules. Ooh. Okay, and this is kind of a common examples and kind of started from supermarket sales data. And so what they found is, say, people buy baby nappies, they often buy a beer together. Okay, so if you look at, so if you say, if you run the supermarket and you have these records of all the people and what they buy, and you might start find, okay, customers who buy nappies, maybe, and also buy a beer. Okay, and then if you look at this group people, and then you can see, so the people make these purchases are mostly by men, and they actually has a specific time when they do these purchases, Friday between 6 p.m. and 7 p.m. Okay, and so these are kind of reasons to explain. So why the men, when they make a, say, when they do shopping on Friday between 6 a.m. and 7 p.m., they would buy nappies and beer together. Okay, so this is just one possible explanation, not say the correct answer. Okay, so for example, because the nappies are big, so these are usually comes in big packs. So the wife would let the husband to do the purchase so they can carry it. And because it's end of the working week, and the husband probably also want to get some beer for the weekend as well. So this is one of the hypotheses, something say why there's lots of men would buy nappies and beer together in the evening of Friday. Yeah. Okay. And so what then, if that is true, or there's this kind of pattern, so the supermarket, what they do is they put the more expensive beer next to the nappies, and because they know these are the husbands buying nappies for their baby, but also they would like to pick up beer, so they put the more expensive beer there, so to improve the profit. So because now there's more people buying more expensive beer. Okay. And this type of analysis is called the basket analysis. And so the basket means the shopping basket. And so analyze the basket of all your customers. So all the shopping records of the customers. So this is how you find these patterns, say, in Friday evening, people buy beer together with nappy. That's something you would done, or the result of the basket analysis. Okay, and then the rules you find as a result of this is called association rules. So people buy beer, also buy nappies in Friday evening. I think the other common ones is, say, people buy beer, also buy peanut, because these are two things people. And peanut people usually have it when they drinking beer. Okay, and this is also something, for example, used by online shops as well, not just supermarket. So this is Amazon, and this is maybe a little bit old interface now, but it will explicitly tell you, okay, for the people who buy this book, also buy these things, or maybe these things, and in the hope that you might pick one of these as well. Okay, and here I'm gonna, so it looks like quite a bit of math, but it's actually not too bad. Okay, and so first we have a database of all the transactions, so all the purchase records of your customers. And so the entire collection is called Big T, and then each of these are each of the transactions, each purchase. And each of these purchase and contains a number of items. So usually when people go to a supermarket, they buy more than one things. Okay, and so for each of these T, and it have a collection of items and called I1, I2, IM, so M items for each purchase. Okay, for the association rules, they want to find patterns, associations, correlations, or causal structures among the items. For example, so the patterns and associations is quite kind of generic. And correlations means and two items are always bought together. And in this case, for example, beer and nappy, they have a strong correlation. People buy beer, also buy nappy, and maybe not all the time, mostly just in Friday evening. And then the causal structure is a bit more difficult. And that means the two items not just correlated but one thing causing or another thing happened as a result of the first one. Okay, so that's a bit harder to do. But I mean, sometimes the causal structure also just appear as a correlation because one thing always causes the other, and then these things appears to always happen together. Okay, and then so this is kind of relations we want to find. So you have two products, one is bread, the other one is milk, and you want to see in general how many customers buy both. So obviously, the larger the overlap, that means the stronger the correlation between these two products, and that can be treated as association rules. And you set a threshold, say if it's above 50%, then we can call this and the two associated. And at the shop, you want to maybe put the milk and bread together. Okay, and then there is some terms, and in terms of evaluating how strong this correlation is, how strong the association is. So the first is the support, and that means the transactions that contains both X and Y. So that means these are all the transactions that contains both milk and bread, and is the percentage was in terms of the total number of transactions. Okay, and then so that's the support, and then for confidence, and it says is how often one items appear in the transactions of that appear in transactions that contains X, Y appears in X. So in this case, it says it's this part divided by all the people by beer, that's 3/4. And you have a similar number for milk, so you can say the overlap part is among how many people buy milk, but also buy beer, who also buy bread. Yeah, maybe that's a bit easier. So you can say the confidence is what percentage of people buy bread, also buy milk, and it's sometimes a different number compared to what percentage of people buy milk and also buy bread. That's confidence. And support, and would be that people buy both milk and bread divided by all the people buy either bread or milk. That makes sense. That's only one number. Okay, and so this is how you write the association rules. And so it says, if you buy something with, if you buy diapers or nappies, you also buy beer. The support, which is out of the total transaction and is 0.5%. So that's not particularly high. But the confidence is 60%. So that means 60% people who buy diapers also buy beer. That's a quite high correlation. And then similarly here, it says a student study computer science and study database module. They got grade A. They have a correlation of 75%. That's actually quite high. Okay, and so the association rules mining, or the AR mining, which stands for association rules mining, is to find all such rules. So you set a minimum support and a minimum confidence. And so the minimum support to ensure there is a significant amount of transactions which fall into this. And for example, you might have a very high correlation between these, particularly to say between the diapers and the beer. But the total number of these kind of transactions is very small. It only happens once every week. And even it's 100% correlated, it's not particularly useful. It's a very small, a very kind of uncommon event. You want to make sure that in total there's a large number of common and examples of transactions as well. And then the support and for the confidence, and you want it to be as high as possible. That means a strong correlation between these two. The things people are much more likely to buy together, for example. And then you can set a minimum value for both. And then you can just compare every possible pair of products, or maybe even three, a group of three. In this case, say, and people buy beer and, diapers and beer are more likely to buy peanut, for example. And you can have, so basically it does not always 1-to-1, it can be 2-to-1, 3-to-1, etc. And so on and so forth. Okay, and to do this, you can list all the possible associating rules, all the possible pairs or groups or products, and then you compute the support and confidence for each of them, which will be, this will be actually a lot. And if you have 10 products, and you will have more than 100 different possible associated rules. And then you filter out one, and you calculate the confidence and support for each rule. And then you filter out those ones which does not meet the minimum standard. And this will take a long time to compute, and just because there are many possible groups of products. Okay, and the other way would be you actually just only generate all the item set with the minimum, at least the minimum support. So these are actually quite frequent transactions, or type of transactions. Say the beer and nappy is quite frequent transaction. And then if that's the case, and then you try to calculate the confidence. If it does not even meet the support criteria, you don't need to even calculate the confidence. Okay, and then so this is where the things get a little bit complicated when you generate these association rules. You first pick the items that at least has enough support, so that these are quite common to popular products, and then you calculate their confidence. So, and then you have, so for the so first you have a rules which involve two items. Then you would have A, then you would have A, B, A, C, A, D, A, E. That's this one here. And then B would have B, C, B, D, B, E here. And C have C, D, C, E, and finally D, E. And you have to calculate the confidence for all these rows. Okay. And then once you're done for the second one, sorry, for the 2 item rows, and it goes down to the 3 item rows. As you can imagine, there's even more, and it goes down to the 4 items rows. And finally, the rows with all the products, okay? So even just for 5 products, you have a lot to calculate already, okay? And then the general rows, you have 2 to the power of the possible candidate set. And so each of these are possible an item set or group that you need to calculate the confidence and support. And D here is the number of products. And so 2 to the power of D, so you can imagine as the number of D increase, and this number becomes very big, and it becomes very time consuming to compute all the rows. Okay, and also there's a lot of duplication. You can see these rows involves the same 3 product and just grouped differently in a 3 times in a 3 item row. Okay, and then so as already mentioned, and the brutal force will be calculated. So first create all the possible item set with 1, 2, okay, with 2, 3, 4, anything more than 2 or more items in it, and then becomes the candidate, and for each of them, and you calculate their confidence and support, and then check if it meets the requirements. As we said, it's going to be very expensive to calculate. Okay, and you can also, but instead you probably want to try to reduce the number of things you have to check. Okay, and you can either reduce the number of candidates, so number of the things you want to check, or you reduce the number of transactions you want to check, or you want to reduce the number of comparisons. Just basically calculating the confidence and support. Okay, so this is one of the things that's important. It says if an item is infrequent and all its superset should also be infrequent. And so what it means is saying, for example, if A and B is found out to be not frequently linked together or does not meet criteria, and all these other ones, which including A and B, can be excluded. Because if we know A and B is not a popular combination, then all these ones will not be a popular combination because they all including A and B in it. And we already know A and B are not popular together. Okay, so what you do is you first generate all the popular ones. So basically, you first calculate the popularity of all the two item set, and you remove those which are not popular, like A and B, maybe B, C, maybe C, D, C, etc. And then you don't need to calculate for the three items set. You don't have to calculate anything that is already pruned. For example, if it's A, B is removed, and these don't have to be calculated again. And if BC is removed, then these ones, everything including BC can be excluded further for the three set, and so on and so forth. Okay, okay, I think that's it. So that's the idea of the association rules and how to calculate. And maybe the main message is actually it's a quite expensive and calculation, and you need to, because the number of possible rules are very large, and you need to be careful when you to do this kind of thing. Okay, and we still have a little bit of time, and so I just want to go through the requirements for the last coursework. So you can see it's here. Requirement here. So that's submission page, and then there's this PDF file. So that's the actual requirement, and which I already have on my computer. I just need to open it up. Oh, not this one. This one, yeah. Okay, so this is the requirements for the last coursework, and it's mostly using KNIME to create a data analysis workflow. And so 25 marks, and deadline is the end of next week, Friday. So it's an individual work, and you need to pick one data set from here. So the link is there, you can click and go to the website. And so this is where we get this, say, and the pedal, the iris data set, which including the sepal and pedal width and length, etc. And then many other ones. I think car data set is also here. Oh no, it's not exactly the same. Okay, but anyway, and there are lots of data set here. So these are the popular ones. Yeah, you can actually use this one, and it says the beta version, which give you a better look at the view. And you can either search for a particular data set, or you can just view data set. And then we'll give you a list of the view, and you can filter here. So for example, you filter by business, and these are all business data set. Okay, and for the coursework itself, and you can pick any data set you want, and no particular rules, just pick any data set from there. And it's useful to include in the report saying which data set you used. Okay, and then you design a visual analytics workflow in KNIME to analyze the data set. So the workflow would start from importing the data and doing data mining, this including classification, association rules, clustering, and also then the visualization. Okay, and so the data preprocessing, so including importing the data, change the format, mapping and categorical values to numerical values, and fill in missing data, so on and so forth. Data mining, I already said, can be, say, classification, prediction, clustering, association rules, so on and so forth. And then the visualization. And in terms of visualization, we covered different type of charts before, so you should know. Okay, and then you need to create the workflow in KNIME, but you don't need to submit the KNIME file actually, and you just need to including a screenshot of your workflow, and just to make sure the text on the screenshot is clear enough to see, because we're not seeing the actual workflow files. So don't be too small, make sure, and the people marking your work can actually read the text. Okay, and also you probably need more than one screenshot. You might have a screenshot of the overall workflow, and for example, you might want to explain what data processing you did, and you want to show the results of data processing as well. And that involves opening up the results of a node or step, and that probably needs a separate screenshot. So including as many screenshots as you need to make sure. Just imagine someone look at the report and they don't never seen workflow before. They need to understand what you did. So including as many screenshots as you need. Okay, and so also need to explain and what kind of analysis you're trying to do. And then how does your workflow help achieve the goals? And so why did you say do a clustering using Kmeans? Also, why did you use Kmeans? You didn't use, say, the hierarchical clustering or the density-based. Why the Kmeans is better for your case? And then finally, any things you found and from your analysis. I don't know, say, depends that again, so this really very much depends on the data you choose. And if you choose the car data set and you say, this is the, these are the cars which are most fuel efficient, that's what you found, for example. And then one extra mark for the presentation. So in terms of the report, the formatting and writing of the report. Yeah. So to answer, so I would recommend to address each of these points. Okay, so the point about data processing. So you write down what you did in terms of data processing and show the results of data processing with a screenshot. Similar here. And you want to explain what are the goals, at least explain. This one probably don't need a screenshot. But then these ones definitely need. You want to show how the data processing, mining, or the validation help with achieving your goals. And this one probably you need a screenshot as well. You have to say, what is the finding, why it's interesting, how you can see the findings from your results. Yeah. So into a screenshot of your workflow, but also the text and screenshots to justify designs. And that means redress into all these different points. And okay, is there any questions regarding the coursework?
Yeah, I have a question.
Yeah.
So I was going to ask, this text is okay. Is it okay to, have a Word document to, explain the text and screenshot, or do you expect us to explain everything in our KNIME document?
No, and Word document is fine. I think that's what's expected, because you are only using screenshots and text, and you don't actually including the KNIME file. So you don't. So I mean, if you want to add some text like annotation in KNIME, that's also fine. But you don't have to. You can do that in Word as well. That's fine.
All right, thank you.
Okay. Any other question? If nothing for now, you can still ask and have a look, and maybe have a look at the data set as well. If you haven't started, we also got a lab later in the afternoon, and you can also ask a question then. Yeah.